Hi there, guys. Welcome to AP Biopharma with Dr. D. And in this series of video tutorials, we're going to be talking about energy and life, or bioenergetics and enzymes. Specifically, we'll be covering topics 3.1 to 3.4 of your syllabus. So, energy and life. The living cell really is a miniature chemical factory where thousands and thousands of reactions occur at any time. The cell will extract energy from these chemical reactions and apply the energy to perform work. For the most part, when we talk about energy in life, we talk about chemical energy or the energy contained within chemical bonds. Energy is needed to drive reactions as well as other processes which are essential to life. So, what are some of these processes that require energy? The first one is biosynthesis. That is the synthesis, the putting together of large biological molecules such as proteins, nucleic acids, DNA and RNA, carbohydrates, and lipids. These are needed for growth and maintenance. Synthesis of these large biological molecules requires energy. The second category of processes that require energy is mechanical work. This is usually a physical change in the position of a cell or part of a cell. And of course, at the organismal level, an organism moves, muscle contraction. The third category is concentration work. Concentration work is the movement of materials against their concentration gradient. That is active transport, with which you're already familiar with. Fourth category is electrical work. That is the maintenance of the membrane potential, which is crucial, especially for neurotransmission. Fourth category is the generation of heat. Endotherms, warm-blooded animals, maintain relatively constant body temperature by the generation of heat. And finally, a few living creatures generate light, also known as bioluminescence. That is another process that requires energy. For the most part, energy that living organisms obtain comes directly or indirectly from the sun. So most energy comes from the sun. Organisms differ in the modes in which they obtain energy. We have autotrophs and heterotrophs. Autotrophs are able to harness and store energy in food to make their own food. Heterotrophs need to consume other organisms to obtain energy, to obtain food. So autotrophs make their own food, heterotrophs need to consume other organisms. Autotrophs are two types. Photoautotrophs, with which you're familiar with. These are photosynthesizing organisms. They use the energy of the sun to make food. And there's also these weird little creatures called chemoautotrophs. Chemoautotrophs play an important role in creating ecosystems in the depths of the oceans where no light can penetrate. And whole ecosystem exists because of chemoautotrophs. Chemoautotrophs are these microorganisms that can use gases, inorganic gases released from volcanic vents deep in the ocean, and using redox reactions of these inorganic compounds to obtain energy, and then they use this energy to make their own food. Now, the flow of energy drives all life processes. And I would like to remind you that energy is subject to the laws of thermodynamics. And the first law of thermodynamics states that energy cannot be created or destroyed. It can be transferred from one system to another or transformed from one form to another, but it cannot be created or destroyed. The second law of thermodynamics states that every energy transfer or transformation increases the entropy of the universe, where entropy is a measure of disorder, chaos. The flow of energy in living organism is subject to these laws of thermodynamics. For this reason, an ecosystem must constantly have an input of energy. Energy enters an ecosystem, for the most part, through solar energy, the energy from the sun, and leaves the ecosystem as heat loss. One form of energy is transformed into another. The electromagnetic energy from the sun is transformed into chemical energy and heat. and lost as heat. The energy transformation in living organisms, as I said, are subject to the laws of thermodynamics. And let's review a few key terms. A closed system is a system which is sealed from its environment. It cannot take in nor release energy. Think of a thermos, one of those thermos flasks. If you put a cold beverage in it, it'll remain cold for the remainder of the day. If you put a hot beverage in it, it'll remain hot. That is because this is a closed system. It is sealed. It does not exchange energy with its environment. Most systems, however, are open systems. Living organisms are open systems. They can have energy added to them or removed from them. So let's review the first law of thermodynamics. Energy can be transferred and transformed, but it cannot be created or destroyed. So the energy that leaves a system must equal the one that entered plus the amount that remains. So the equation has to be balanced because energy cannot be destroyed or created. So however much energy I consume, some of it will remain in me, the rest of it must leave my system. And it all has to add up. The total energy which is now stored within a system that stays within me is called internal energy, or E. Now, any change in the internal energy that occurs during some process is depicted as delta E. Delta, the Greek sign for change. In living organisms, the conditions under which we operate do not change. We maintain homeostasis, so we do not change. There are not any large changes to volume or pressure. And for that reason, we can simply say that E, the internal energy, is actually H, enthalpy. Enthalpy really is related to E, but it's dependent on pressure and volume. But because there are no changes in pressure and volume, in living organism, we don't talk about E, we talk about H, or enthalpy. H is also sometimes referred to as the heat content of a system. Now, if we're talking about chemical reactions, the change in H really can be either positive or negative. And the change in H really is the difference between the energy of the products and the energy of the reactants. When delta H is negative, a reaction is said to be exothermic. That means the reaction releases heat. It proceeds with net release of heat. Think of burning of a gasoline in a car. When delta H is positive, a reaction is said to be endothermic. That means the reaction absorbs heat. So an endothermic reaction is if you were to take out an ice cube from your fridge and leave it at room temperature, that ice cube will absorb the heat from the surrounding air of the room and melt. That's an example of an endothermic reaction. We need to add heat to the ice cube so the ice cube can change phase, go from solid to liquid. Now, H applies to any type of process. It doesn't have to be a chemical reaction. It could be a physical change, like in the case of the ice cube. Let's introduce another term from thermodynamics, and that is entropy. So the direction of a spontaneous reaction and what it takes to go the other way can be measured by the change in entropy. And the example I'm showing you here is both an analogy and not an analogy. It's actually a literal representation of entropy. So on the left, you will see a boy sitting at its desk. It is his desk in a highly ordered and clean and organized room. On the right, you will see that same room, a complete and utter mess, chaos. So what does it take to go from the picture on the right to the picture on the left? It takes effort. It takes energy. Someone needs to come into that room, bend down several times, pick up things, think about where to put them, reach up, reach down, reach across, spend time, effort, energy to organize and clean this room. So it takes a lot of time and effort and energy to go from the picture on the right, which is chaos, to the picture on the left. On the other hand, if the boy, its parents, the housekeeper, the cleaning lady, whoever it is, do not do anything, if no human being does anything, no effort, no energy, no time spent, over time, slowly, that ordered room is going to turn into chaos. So the reaction from order to chaos is spontaneous. It requires no effort and no energy. The opposite is not spontaneous. It requires energy. And this is basically how the universe works. Now think of it this way. We are made up of cells. We have organ systems, organs, tissues, cells. Cells are made up of organelles. Organelles are made of macromolecules, biological molecules. Large biological molecules are made of smaller molecules. It's monomers. There's even smaller molecules, and then there's atoms. The further down we go, the less order there is. So human beings are highly complex and highly ordered. It requires a lot of energy to maintain that order. Living organisms are highly ordered systems, highly complex, and require constant input of energy to maintain that order. If that energy ceases, eventually, spontaneously over time, that organism is going to disintegrate into chaos. It's going to die. So entropy really tells us whether a process can proceed. It can be measured in changes in entropy. Entropy is a measure of randomness, of disorder, of chaos. Entropy increases when a system becomes less ordered and vice versa. The change in entropy of the universe is a positive number for every spontaneous process or reaction. But in the specific system involved, that may not be the case. And for that reason, in living organisms, we use another term, free energy. We use the term free energy to measure whether a system is, whether a process is spontaneous or not. So what is free energy or Gibbs free energy? Free energy is a readily measurable indicator of spontaneity, whether a process or a chemical reaction are spontaneous or not. Every spontaneous process, every spontaneous reaction is characterized by a decrease in free energy of the system. A living system free energy really is the energy that can do work when the temperature and pressure are uniform, as in a living cell. The change in free energy during a chemical reaction or during a process is the difference between the free energy of the final state and the free energy of the initial state, or the difference of the free energy of the products and the reactants. So what is the relationship between free energy, enthalpy, and entropy? The formula that I'm showing you here, you're not required to know it, but I'm showing it to you so I can explain to you those concepts because you are required to understand how these concepts relate. Think of H, again, enthalpy, as the total energy, the total internal energy of a system. If you subtract from that total energy the entropy, the energy needed to maintain order, whatever remains is free energy. It is energy that can be used to do work. Only processes with a negative delta G are spontaneous. Spontaneous processes can be harnessed to perform work. And free energy really is a measure of a system's instability, its tendency to change to a more stable state. Normally, a system that has a lot of free energy is an unstable system. It tends to want to change that instability. It tends to want to go to a more stable state. So it tends to want to go from high free energy to low free energy. Therefore, delta G will be negative. When delta G is negative, the free energy decreases and the stability of the system increases. So if you start with a lot of free energy, that system is not very stable, right? It's less stable, but it has great work capacity. It has the capacity to do work. It has the capacity to move to a less free energy, lower G state, which is a lot more stable, but it also has less work capacity. But in the process, free energy is released, and that free energy can be used to do work. So when we talk about chemical reactions, not necessarily processes, but specifically chemical reactions, on the y-axis, we have free energy. On the x-axis, the process of the reaction. If the reactants have higher free energy than the products, then the reaction is spontaneous. Delta G is negative, and the reaction is said to be exergonic. Exer from exit. It proceeds with a net release of free energy that can be used to do work. The magnitude of delta G represents the maximum amount of work that can be done. If, on the other hand, the reaction here in the blue graph, the free energy of the reactants is lower than the free energy of the products, then that reaction is non-spontaneous. It requires input of energy. We need to supply it with free energy. And the magnitude of delta G, which is now positive, is the quantity of energy which is required to drive this reaction. So how do we make the blue reactions happen? We make the blue reactions happen by using the energy released from the orange reactions. So reactions that release energy can be used to drive reactions that absorb energy. We're going to talk about this in a few minutes. Another term that I would like to introduce you is metabolism. Now, despite the popular use of the word metabolism in everyday language, metabolism isn't simply how we digest our food. Metabolism are all chemical reactions in an organism, not just the digestion of food we eat. Metabolism is the sum of all chemical reactions that happen in an organism. And metabolism is not simply a collection of isolated chemical reactions. It's more of a collection of metabolic pathways. Pathways are a series of sequential chemical reactions. They begin with a specific molecule and end with a product. And each step of the pathway is catalyzed by a specific enzyme. Metabolic pathways or metabolism has two sides of the coin. One side are the catabolic pathways, which release energy. Catabolic pathways are breaking down of complex molecules into smaller compounds. So that is the digestion of food, for instance, is an example of a catabolic pathway. Anabolic pathways, the flip side of the coin, consume energy. They consume energy because they're required to build complex molecules from simpler ones. So catabolic pathways release energy and are the breakdown of complex molecules. Anabolic pathways consume energy because they build complex molecules from simpler ones. Okay, you need to know these two terms, anabolic pathways and catabolic pathways. At equilibrium, let's remind ourselves what equilibrium is from chemistry. At equilibrium, the forward and reverse reactions occur at the same rate, and it is the state of maximum stability. A process is spontaneous and can perform work only when it is moving towards equilibrium. And if you have a closed systems, all reactions will eventually reach equilibrium. But once they reach equilibrium, no work can be done. This is equilibrium is maximum stability, minimum work potential. So at equilibrium, there's really no net flow of matter because however much products you make, you also revert to the reactants, and no energy is being produced. So this is really, equilibriums are really not useful for living cells. So living cells are characterized by continuous reactions, and they maintain themselves in state far from equilibrium. Because remember, at equilibrium, you're at perfect stability, but you also cannot do any work. You cannot create energy, or produce energy, not create. Cells maintain a steady state in which reactants and products and intermediate steps are kept at levels very far from equilibrium. And this is possible because we're open systems. We constantly receive large amounts of energy from the environment. We receive materials from the environment. And energy and materials are being also removed from us. So there's a constant flow. And I'm going to give you the following analogy. If you take a vessel, a container that has an opening at the top and an opening at the bottom. And if the rate at which you pour water into that vessel equals the rate at which the water flows out, at equilibrium, the volume of the liquid is not going to change. Nothing is happening. You're in equilibrium. Now, that is not a good state to be in if you want to do work. So living cells, processes such as concentration gradients, transport across membranes, chemical reactions never reach equilibrium. If the concentration of glucose on both sides of the membrane in a cell reaches equilibrium, then no more glucose can be transported inside the cells. We don't want that. So always remember that a living cell is never at equilibrium. So how do we get things done? How do we extract energy? How do we manage our energy resources? We do this by energy coupling. And the word coupling comes from the word couple. Couple means two. Who are in that couple? And that couple are the two types of reaction. The exergonic ones, the one that produce energy, delta G negative, and the endergonic ones, the ones that require energy, delta G is positive. When you put them together, the one that produces energy can help drive the one that requires energy. So coupling of exergonic and endergonic reactions helps cells manage their energetic resources. So anabolic processes, which build organic molecules and require energy, are coupled to catabolic processes, which release energy and break down large molecules. Usually this coupling is not direct, but it's mediated by the synthesis and hydrolysis of ATP. So most energy coupling in cells is mediated by ATP. ATP, adenosine triphosphate, is a nucleotide, I'm going to remind you, that it's composed of the nitrogen-containing base adenine, a ribose sugar, and 3 phosphate groups. As such, ATP is also a component of RNA molecules. Hydrolysis of ATP into ADP and inorganic phosphate releases energy. Synthesis of ATP from ADP and inorganic phosphate absorbs energy, requires energy. So the forward reactions ATP to ADP is exergonic. The reverse reactions ADP to ATP is endergonic. And here is an example of how this works. If we want to turn glutamic acid, which is an amino acid, into a different amino acid, glutamine, we need to add ammonia to it. That reaction requires about 3.4 kilocalories to proceed. So it's an endergonic reaction, delta G is positive. In order to do this, we're going to use ATP hydrolysis to power this reaction. ATP hydrolysis produces a phosphorylated intermediate. And in a second step, this phosphorylated intermediate now is turned into the final product. So the two reactions are coupled. ATP hydrolysis and the synthesis of glutamine are coupled. ATP hydrolysis releases 7.3 kilocalories per mole. The synthesis of glutamine requires 3.4, so there's plenty of energy and some to spare. Okay, so the total free energy change for the coupled reaction is negative. So when you couple these two reactions, the net delta G is negative, which means these reactions are now possible. They're spontaneous. ATP gets regenerated, and this is a review from what you've learned last year, but I'm just reminding you, it gets regenerated. ATP into ADP is when you require energy to drive a process. When the process creates extra energy that we need to store, we're going to store it in the ATP molecule by turning ADP into ATP. So the energy to phosphorylate ADP really comes from catabolic reactions in the cell, whereas the energy that needs to drive anabolic reactions comes from ATP hydrolysis. The ATP cycle is a revolving door through which energy passes during its transfer from catabolic to anabolic pathways. So ATP is a crucial molecule and cellular metabolism. And this is, guys, where we're going to end. We're going to continue next class with enzymes.